Section: Introduction. In this section, we introduce Jamba 1.5, which includes two new large language models based on our Jamba architecture, now available for public use. Jamba-1.5 Mini is an updated version of our earlier Jamba release, while Jamba 1.5 Large features a hybrid architecture that combines Transformer and Mamba layers, along with a mixture of experts, module. Our previous work has shown that merging Transformer and state space models is beneficial, and Jamba 1.5 Large showcases these advantages at a much larger scale, with 94 billion active parameters out of a total of 398 billion. Despite its size, Jamba 1.5 Large can run on a single machine equipped with 880GB GPUs when processing a context of 256,000 tokens, thanks to the efficiency of our architecture and a new quantization technique we developed. Both models have been instruction-tuned to enhance their capabilities, and our evaluations indicate they perform similarly to other models of their size while benefiting from the efficiency of the Jamba architecture. Notably, Jamba 1.5 models excel in long context evaluations, being the only models effective at 256,000 tokens on the ruler benchmark, while also significantly reducing memory usage and improving throughput and latency. We make the Jamba 1.5 models available under the Jamba Open Model License. Jamba 1.5 Large retains the same structure as Jamba but with increased capacity, featuring 94 billion active parameters and 398 billion total parameters. It consists of several blocks, each with a specific number of layers and an optimal ratio of attention to Mamba layers, which we confirmed through our research. Instead of using a single multi-layer perceptron every 10 layers, we employ Mo with 11 experts, selecting the top 12 for each token. We compare the Jamba 1.5 models to other publicly available models of similar sizes, noting that Jamba 1.5 Mini has a comparable number of active parameters to Mixtral 8x7b, while Jamba 1.5 Large falls between LLAMA 3.1 to 70b and Mistral Large 2. Our models also use significantly less memory for KV cache compared to others, achieving about a tenfold reduction. With our specialized quantization, Jamba 1.5 Large can be efficiently served on a single machine with 880GB GPS for context lengths up to 256,000 tokens. Additionally, we explored Mamba 2, a faster version of Mamba, but found that the combination of Mamba 1 and attention layers performed better in our hybrid architecture. We believe this is due to the full attention layers effectively pooling information from the entire context, making the advantages of Mamba 2 less impactful. We also share insights on serving Jamba models efficiently at scale. To support Jamba 1.5 Large, we developed a new quantization technique called Experts int8. We found that over 85% of the model weights are in the Mo layers, and over 90% are in Mo or MLP layers. Our approach quantizes these weights to int8 while maintaining the benefits of fast BF16 kernels. The dequantization occurs within the fused_Mo kernel, adding minimal overhead and even improving latency compared to BF16. Our Experts int8 method offers several advantages. It is quick, does not require lengthy calibration, allows for large activations in BF16, and is compatible with A100 GPUs. It matches FP8 latency on H100 GPS and significantly outperforms other quantization techniques on A100, making it an appealing option for serving large Mo models. Section Summary. In this section, we introduce Jamba 1.5, a set of large language models that utilize a hybrid architecture combining Transformer and Mamba layers, achieving significant efficiency and performance, particularly in long context evaluations. We also present our novel Experts int8 quantization technique, which enhances serving efficiency while maintaining low latency and high quality. Section: Activation Loss. In this section, we discuss our findings regarding activation loss during pre-training. We observed that certain activations, particularly from specific experts and the last Mamba layers, increased significantly for some input tokens, reaching values as high as 23. While this did not negatively impact the pre-training, which we conducted in BF16 precision, it could lead to numerical issues during inference since some quantization libraries only support FP16 precision, with a maximum range of 64,000. To address this, we introduced an activation loss term that is proportional to the mean square of the activations during the forward pass, with a configurable factor of 24, which penalizes larger activation values. Our experiments showed that this auxiliary loss did not affect training, even with values up to 25. For Jamba 1.5 large, we set the factor to 26, which effectively reduced the activations to a more manageable range of 2,000 to 3,000. Additionally, this auxiliary loss quickly lowered the activations, allowing us to implement it towards the end of training without impacting speed or quality. We validated this method by running our evaluation suite on the model using FP16 activations, achieving results consistent with BF16 evaluations without any numerical issues. Next, we analyze throughput and latency. Thanks to our hybrid Jamba architecture, the Jamba 1.5 models demonstrate excellent performance in these areas. Our figures illustrate that Jamba 1.5 mini and Jamba 1.5 large outperform similarly sized models, especially in long contexts, where we see significant advantages. Notably, Jamba 1.5 large operates efficiently even with long contexts, unlike the larger Llama 3 to 405B model, which cannot run on the same hardware. Regarding training infrastructure and data, we trained Jamba 1.5 large on NVIDIA H100 GPS using our proprietary framework, which incorporates various parallelism techniques. The training occurred in 3 stages. Initially, we pre-trained the model on an in-house dataset, last updated in March 2024, which includes a mix of publicly available web documents, code, books, and scientific articles. Our pre-processing pipeline involved parsing, quality filtering, and deduplication, utilizing our in-house parser to extract text and formatting. The dataset emphasized multiple languages, including English, Spanish, French, Portuguese, Italian, Dutch, German, Arabic, and Hebrew, and included a phase focused on long documents to enhance long-range capabilities. In the post-training phase, we aim to achieve 2 goals: equipping the model with various skills and conversational abilities while retaining the long context capabilities developed during pre-training. Since most post-training datasets consist of shorter examples, we employed supervised fine-tuning on high-quality conversational data, skill-specific data, and long context data. This mix was designed to maintain long context capabilities while acquiring new skills. Our evaluations indicate strong performance in long context scenarios. We also utilized synthetic data extensively during supervised fine-tuning, reflecting our structured data approach for building compound AI systems. We developed various data synthesis pipelines targeting different model capabilities, following a consistent pattern of sampling prompts, generating responses, filtering by quality, and post-editing for formatting. We selected our final training recipes based on a range of internal automatic metrics. Both Jamba 1.5 models were fine-tuned using the same control tokens and formatting template, which we provide as part of our release, compatible with Hugging Face tokenizers and chat templates. Lastly, we generated tabular data and corresponding question-answer pairs, as shown in our work on table understanding. We converted these tables into natural language paragraphs using a language model, creating training examples that included extraction, aggregation, and attribution tasks related to specific rows or columns in the tables. Section Summary. In this section, we address the issue of increasing activation magnitudes during pre-training by introducing an activation loss term to penalize large values, ensuring numerical stability during inference. We also detail our training process for the Jamba 1.5 models, which includes a three-stage approach that combines diverse datasets and techniques to enhance long context capabilities and conversational skills. Section: Document QA. In this section, we discuss our approach to document question answering. We prompt a language model to create question-answer pairs from a document, whether it consists of a single paragraph or multiple paragraphs. To enhance understanding of longer contexts, we sometimes include similar texts alongside these examples. For tool use, we start with the open-source glaive function calling dataset, which we filter using various methods to ensure the output is valid. We generate multiple valid parameter assignments for each function in glaive and then sample subsets of these assignments to create user requests for function calls. We prompt a function calling language model to respond to these requests, keeping only those responses that match the original parameter assignments. Regarding steerability, we established a set of clear instructions that can be validated. We created prompts for document drafting tasks with added constraints and generated responses from a language model. We used rejection sampling based on our detailed instructions and a general reward model. To incorporate instructions into system messages, we reformatted prompts into a multi-turn conversation, placing the instruction in the system message. We also share some observations from developing Jamba 1.5. Although we used a small amount of non-English data during post-training, our models perform well in multiple languages, likely benefiting from the multilingual data used in pre-training. Our efficient Jamba architecture reduces the cost of fine-tuning on long contexts, allowing us to explore various training methods. We found that while preference tuning algorithms improve alignment with human intent, a combination of careful data generation, filtering, and supervised fine-tuning is essential for a strong post-trained model. In terms of evaluation, we acknowledge that benchmarks only partially reflect real-world success and user satisfaction, yet we report results on key public benchmarks. We present results on standard academic benchmarks, chatbot benchmarks, and long context evaluations, comparing Jamba 1.5 large with similar-sized models like LLaMA 3.170b and Mistral large 2 to 123b, as well as Jamba 1.5 mini with Llama-3.1-8b and Gemma 2 to 9b. For academic benchmarks, we report results across various standard tests, including MMLU, GPQA, and Human Eval, among others. We also evaluate on instruction following and function calling datasets, along with safety evaluations. Our findings indicate that Jamba 1.5 models perform comparably to recent state-of-the-art models on academic benchmarks, demonstrating strong capabilities in knowledge, reasoning, instruction following, and function calling, while also maintaining good safety metrics. In chatbot evaluations, we assess Jamba 1.5 models in two scenarios: Arena Hard, which includes challenging user queries judged by GPT-4 Turbo, and Wild Bench, which also uses GPT-4 Turbo with length bias mitigation. Our results show that Jamba 1.5 models perform excellently, with Jamba 1.5 large outperforming LLaMA 3.170b, though it slightly trails behind Mistral large 2 to 123b, which has about 30% more parameters. Section Summary. In this section, we describe our approach to generating question-answer pairs from documents, utilizing a function calling dataset for parallel requests, and implementing steerability through structured prompts. We also share observations on the multilingual capabilities and efficiency of our Jamba 1.5 models, report their performance on various academic and chatbot benchmarks, and highlight their competitive results compared to other state-of-the-art models while maintaining better throughput and latency. Section: Long Context Evaluations. In this section, we evaluate our model's ability to handle long contexts, specifically up to 256,000 tokens. We assess its performance using both synthetic and natural benchmarks. For the ruler benchmark, which consists of 13 synthetic tasks designed to test long context capabilities, we find that our Jamba 1.5 mini and Jamba 1.5 large models are the only ones confirmed to effectively manage the full 256,000 tokens. Ruler includes various tasks, such as retrieval tasks with multiple items, a variable tracking task, aggregation tasks for common words, and question answering tasks that incorporate paragraphs from natural datasets. While Gemini Pro reported good results up to 128,000 tokens, we could not replicate these findings, as the model often failed to provide answers or generated refusals. We suspect that updates to Gemini Pro may have impacted its performance. Next, we evaluate our model on the 34-34 bench dataset, which averages 100,000 tokens. We focus on 2 English tasks related to understanding long novels, question answering and multiple choice question answering. Our Jamba 1.5 models perform exceptionally well, surpassing similar-sized models like LLaMA 3.1 and Mistral Large 2. We also conduct a basic evaluation of Jamba 1.5 in non-English languages using the multilingual MMLU dataset. Our results show that Jamba 1.5 mini performs comparably or better than other models, while Jamba 1.5 large shows good multilingual capabilities, though slightly behind its peers. Regarding alignment and safety, we aim to ensure our models align with customer expectations and industry standards. We believe in ongoing collaboration with our customers, allowing them to influence model behavior through additional training and prompt engineering. Our AI code of conduct focuses on aligning model outputs with company values, clearly stating expected behaviors, collaborating with customers, and continuously improving based on feedback. In line with our participation in an OECD task force, we align our work with values-based AI principles, including inclusive growth, human-centered values, transparency, and accountability. We have developed 60 behavioral tenets that reflect these principles, which we will make publicly available. Our commitment to accountability is demonstrated through transparency and engagement with customers and regulators, as evidenced by our high ranking in relevant assessments.